Hello, everyone. Welcome to this course today on multicast and unicast routing. Last week, we concluded on this state here. We saw that in order to deliver multicast data, routers need to keep state information that for every multicast group that they must forward gives the outgoing interfaces, and if there is more than one outgoing interfaces, then the router will have to multiply the packets. And the good idea that's behind multicast is that this multiplication by routers is a good way to do, because instead of having a source replicating 1 million packets to 1 million destinations, if we have many, many hops on the path, then every router multiplies a small number of packets. But if 10 routers in sequence multiply the packet 10 times, if you do it 3 times, for example, you already have 1,000 packets. Right? And if you do it 6 times, you have 1 million packets. So that's the exponential growth of multiplication. That's the idea. However, there's a price to pay, which is that the routers need those routers here as they are presented. They need per flow state. Per flow means per multicast address. And every multicast address is something dynamic and logical. And this can be potentially large. So that defeats a bit the purpose of routing in the internet, where we've seen that we have IP addresses that are reflecting where in the internet the systems are, where we can aggregate multiple destinations that have the same prefix. Here, none of that happens. So we have a scalability issue with multicast. We will see how this is addressed by some routing mechanisms. Precisely routing, so multicast routing. The topic today will be routing. So we start with multicast routing. We will also see unicast routing. The goal of routing is to make these entries that are needed in the routers present. So how does R2 know that it has to forward the packet to R1 and to R4, for example? Routing is part of what we call the control plane. Control plane is the set of control functions that are not strictly real-time. Of course, you need to do them as quickly as possible, but they are not real-time in the sense they are not activated for every individual packet that we forward. So it's the management, but we don't call it management. It's the control of the IP layer and the routers. Multicast routing is a dirty topic. There are tens and tens of multicast protocols. We will see essentially one, PIM. PIM sparse mode, that's the only one that has survived this evolution. And there's another method that doesn't use multicast routing, but is some form of multicast routing, which is called beer, which is what we will see in a second. So those are the only 2 methods that are widespread today. PIM sparse mode is very simple when we use source-specific multicast. With source-specific multicast, remember, the idea is that a multicast group is identified by the combination of the multicast address, which is the destination, and the source address. And in particular, only a given source can send to this group. Then here, the problem of the routers is to create this distribution tree. And with PIM-SM, the idea is simple. We use the reverse path. So by unicast routing, by the management of the routing tables everywhere in the network, the source S is known to all the routers. R1 has a routing table that says, in order to reach S, I go via R2. Similarly, R2 has a routing table that says, in order to reach S, I go to R5. That's the normal IP routing that are built with the techniques we will see in a few more minutes for unicast routing. So the idea is when an IGMP message is received by R1, then PIM sparse mode will do a PIM message that will say, oh, somebody needs to get the message of of this group here, and I pass the information to the router, which is the next hop for me on the towards the destination S, which is R5, or R2 here. R2 will do the same. R2 will receive this message. So this is not a multicast packet. It's not an IGMP or an ICMP packet. It's a routing protocol packet. This routing protocol, PIM-SM packet, is received by R2, and R2 sees, oh, I need to continue building the tree towards S. So it will, how do I go to S? I go to R5. So we'll send this PIM sparse mode message to R5, and R5 knows it's directly connected to S, so that's the end. R4 will do the same, and when R2 receives a message from R4, R2 knows it already has a distribution tree for this group, so it will not continue to forward it to R5, but it will know I am already on the group, on the tree, so we'll simply acknowledge this message to R4, and this is how the tree is built. So as you see, if we use source-specific multicast, things are very simple. In fact, that's one of the motivations of source-specific multicast. It simplifies a number of things. Source-specific multicast is not always used. In particularly, large companies tend to have multiple servers that are able to send to the same group just for reliability or scalability. If you're Google and you're streaming via YouTube, you don't have one server that's streaming, but probably thousands or hundreds of thousands of servers. So depending on the state of the network, you may use one or the other server. So you may have different, you don't always use source-specific multicast. So in the general case, it's a bit more complicated. I skip the details, you will see. And here the ideas, you need an additional trick, but the ideas are always very similar. This is multicast routing. And this was the state up to 2-3 years ago. And multicast routing has not been implemented very widely. It's implemented, for example, at EPFL. It's implemented on the Swisscom network. But providers tend to not propagate multicast routing outside of their domains for a number of reasons that we will discuss. But one of the main reasons is that this form of multicast routing requires a router to keep per flow state. And the per flow state is dynamic. If somebody starts listening on some part of the network, that may cause the tree to be modified. So all routers may need to change their state, and this may change very frequently as people connect and disconnect to given channels. So the per flow state, one, can be very large. Second is dynamic, so that's a problem. It makes routers look more like bridges where they have non-structured addresses, except if the number becomes very large, it will not work. That's why it is deployed in networks of a given scale. It's deployed, for example, for TV distribution by Swisscom. It's deployed also in EPFL for more experimental purposes. If we want to do more, then the scalability is a problem. This motivates an alternative solution called BIR, Bit Index Explicit Replication, that I will explain in 2 steps. First, I will explain the spirit and the details. The idea is naive and it's very simple. It consists in saying that a multicast packet, first we add a BIR header. So we add an additional header to forward this packet. We will see that we do that a lot when we do IPv6, IPv4, for example. So that's the first thing that was not very much accepted many years ago. So how to forward this packet will be using extra information. This BIR header essentially says which routers this packet should be delivered to. Let me illustrate this on an example. Here is a similar example to the previous one with a source on the right, but to explain BIR, we need more routers, so I have a more complex scenario. So I have here 4 routers on the left, they are pink, and 1 router on the right. They are what are called edge routers in BIR. Like in many complicated protocols of the internet, we make the distinction between edge routers, routers that directly speak to customers connected to hosts, and backbone routers that are probably connected to a few special hosts like network management consoles and things like this, but are not expected to be connected to consumers here. So those are blue routers here. Now, when a packet is sent by S to IP destination M here, so then assuming it's source-specific multicast, so that works for both source-specific and any source multicast, the first thing is we remove the function that PIM sparse mode has, which is of passing the information of whether somebody is listening to the multicast group. Remember, with PIM sparse mode, the receivers do IGMP. Here they continue to do IGMP or MLD if it's IPv6 to inform the router that somebody is listening. So here R1, R3, and R4 know that somebody is listening. With traditional multicast router, routing. It is the routers that will pass the information via the routing protocol. Here we separate the control plane into two parts. Who needs to listen is assumed to be passed by a special out-of-band information. That seems like, okay, yeah, but we cheat. Instead of solving the problem at the level of the routers, we assume we have an application in the background that does it. It is true, but it turns out that for many multicast applications, this is happening anyhow. For example, because if you're listening to Swisscom TV, then the Swisscom TV app knows who is listening to. So there will be, anyhow, this information. There are also other motivations like software-defined networking. So many networks that are not too large size will use separate servers to do the control of the network. And we might see towards the end also that we can use what is called multicast VPN with a combination of BGP and MPLS that achieves the same thing. So if we ignore those details, so let's assume when you connect to a given channel, then that information is passed to a set of control using a web server, for example, saying there is somebody here who wants to listen, and that information will be translated into the fact that when router 5 has this packet to transmit for the first time, it will poll this service and they will receive the information. What are the edge routers that need the information? So the first change here is we don't speak of end customers, but of edge routers. So this is all internal information inside what is called the beer domain. So R5 now knows that routers 1, 3, and 4 should receive the information. And that's the main idea of beer. The idea is that instead of sending a multicast packet to all the multicast destinations, the first router that receives this packet sends it to all the routers that will need it inside a beer domain here. Okay, doesn't seem to make a big difference, but the difference, as we will see, is what happens in all the other backbone routers here. The first thing to notice is that with beer, the routers must have a number, which is not just their IP address, but is typically a small number, literally 1, 2, 3, 4, like I wrote here. So here, the edge routers are numbered. It's a beer number. It's an additional, in addition to all the IP addresses and Ospf identifiers, etc., they will have a beer number. And this beer number is the sequence of beer numbers. It's put in a clever form that we will see in a few more minutes into an additional header. So before the IP address, we add a beer header that says essentially this packet should go to routers 1, 3, 4. So this is put by router R5. Now, what will router R5 do? Looking at its own Unicast routing table, router R5 is in the same domain as those routers. So it must know that the ID 1 corresponds to the IP address of R1, or whatever way we have to call this router here. And through its Unicast routing table, it can know that in order to reach R1, I have to go to R7. Same thing, in order to reach R3, I will also have to go to R7, and same thing for R4. So I have only one packet to send, so I create one packet with destination header 1, 3, 4. What I presented here gives the impression that this has to be done for every packet, but the smartness and the second main trick of beer is to pre-process this. So this will not have to be done for every packet. So R7, R5 being a beer router, whenever it receives a destination list 1, 3, 4, will automatically and in real time be able to do all this analysis that I presented here. So the packet will be reached to R7. R7 will do the same analysis, which consists in saying, now I have a packet to send to 1, 3, 4. How do I do it? Well, I first need to know how do I go to R1? It's via R6. How do I go to R8, to 3? It's via R8. How do I go to 4? It's also via R8. So from this information, which is only IP unicast routing information, this router can infer a number of things. The first thing is that it needs to make 2 packets because I have 2 next hops. And then also 3 and 4 together, I can reach with 1 packet 3 and 4. So it will create 2 packets with different headers. 2, 1, and 2, 3, 4. And the same thing will happen recursively downstream here. R8 will know that it has a packet to send to R4. R4 receiving the packet will know it is in the destination list. So it presumably has a number of interfaces on which there are subscribers of this group. So it will put the packets on all the interfaces where there was IGMP messages sent. And it also needs to send it to R3. And by doing it, of course, it will remove itself from the header. And the packet will join the other direction. So that's the idea of beer. So in a nutshell, we distribute packets to routers, and we analyze whether we have to split a packet into several, and we update the distribution list. The smart thing is, how can we do that in real time without keeping any per flow information? Once we know we have to reach 1, 3, 4, how do all the routers, in particular the backbone routers, do this processing without having to be bothered with all this IGMP information? And the trick of beer is to use what is called a bit string. That's why it's the bit index. So what I presented as a list of routers will be presented as a bit string. For example, here there are 5 routers in this domain. So the bit string is a string of 5 bits with a 1 in every position where we need to send the packet. If you have 256 routers in your domain, you will need the bit string of 250. If you have 1 million routers, you would need a bit string of 1 million bits. Of course, you will not do that. So you will not have a domain with 1 million routers. The idea of beer is that you do that inside a domain. And when you have multiple domains, then you have interface between domains here with different number inputs. There are additional mechanisms to make it scale to larger things that I will not describe, but you can read that in detail. So let's assume the domain is relatively small. Here it has only 5 edge routers, so we need a bit string of 5 here. Then, for example, if the packet here has to be sent to routers 1, 3, 4, that's the corresponding bit string here. So this is simply re-encoding exactly what I presented before. There's no difference. But of course, the trick is that now it is possible to do all the processing by creating a special table, which is called the beer index forwarding table. That is explained here. So here I'm showing, for example, the beer index forwarding table at router R7. This router is connected to R6, R8, and R5. And the beer index forwarding table contains all the information you need to be able to process any beer header you will receive. So any distribution list you might receive, not just the one that is present here, can be processed by simply looking at this table. And so that means that this table is static. This table changes only when a new router is added. For example, if we add the router R6 and we need to change all the masks and change the table, or when the internal routing changes. For example, if we add a link, if we break the link from R6 to R7, and if we make a link from R7, from R8 to R6, for example, then the forwarding decisions for Unicast routing change, and then this table will change. So they depend only on the information that's available, whether we have multicast or not. That's the main difference. How does it work? Well, here's an example of how it works. So let's assume you are this router R7 and you receive this packet. So this packet has this beer header. Then the beer header will be used to go through the list here. We will analyze which destinations we have by starting with the least significant bit. So we look at the first one that we have. That means destination 1 here. And we go to the row that corresponds to destination 1. So here I have a table with as many entries as edge routers, which is not as many as possible multicast groups. So here, 5 entries. So I go to the first line here, and this line has what is called a forwarding bit mask, that is 0011. Essentially, it is saying that if I go to 1 and 2, I have to go together via R6. Right? This is saying that if I have a packet to send to R1 and R2, I should send it via R6. And this has been pre-processed offline or whenever the Unicast routing has changed. So the rule is I take the destination, which is here. I do the AND of this bit mask. So this bit mask is saying, if I have to send to 1 or to 2, I go to 6. By doing the AND, I will only analyze the destinations that are in my header here. The AND will say that I have to create, I receive this new header here, 0001, which is the intersection of this list here and this one here. That's the way of describing an intersection of lists with bit masks here. So the router R7 will go here, create the new mask, and send the packet to R6. And this is what is done here. Then it will modify, it will see whether I need to create additional packets. This is explained here. So we compute the remaining bit string by ending the original bit string with the inverse of the forwarding bit mask. Essentially, we remove all the destinations that were reached here, and we obtain the remaining thing, which is 0, 1, 1, 1. That is the equivalent of doing the delta operation. I had a set of routers to reach. I remove from this set the ones that I've already found from this first table here. And I obtain 0, 1, 1, 1, 0. And I do it the same process with this one. So I take the least significant bit here, which is bit 3. I go to the entry 3, and I see I do the same thing. That will tell me send the packet to R3. The new mask, the new bit mask, the new bit string will be 0, 1, 1, 1, 0. And then when I do this again, the remaining bit string will be empty, only zeros everywhere, because the delta, because I've sent to all destinations here. So that's the trick of beer. It's implementing set operations with bit strings. And by pre-processing all the tables, it can simply do it in real time. So all the routers here will perform all these operations like they do for IP forwarding. They go to table and they manipulate masks and exactly here. So that's, I think I've explained most of this here. And of course, this doesn't scale to large domains, but multiple beer domains can be interconnected by interconnections, where we have a pink router here and another peak router here. And we'll talk about inter-domain routing when we speak about BGP. Voila, so this is how multicast routing is done today. And the old style, which is still dominant, I would say, in small-scale network, uses PIM sparse mode predominantly. And in data centers or huge infrastructures like Google, Amazon, etc., we use beer. Question? It's a typo, I think. It's a typo. Yeah, it's a bug. Thank you. So you reach R5 when you go to R7 reaches R5 when the next hop destination is R5. That would be R5 here, and that should be R8. Thank you for catching that. So we've seen how to yes? Question? So the question is, here I gave an example with 5. Well, that's a configuration. When you have a beer domain, you need to configure what is the size of the bit string. Here it's configured with 5, which is probably on the lower end. You probably have larger sizes in practice, but it's configured for a domain. And typical values are probably more 32, 64, 128 than 5. But you can configure it in every domain. Yes?
How does the edge router know who is both offended because making all of the line domain?
So here we assume all routers here are beer routers. There are procedures. I give a reference to the RFC. There are procedures to handle the case where R7 would not be a beer router, but R6 would be. So you can handle that. Let's skip those details. Question? In large networks like in data centers, it can be thousands of beer routers. Right? In networks like EPFL, the number of routers is very small. It's a few tens of routers. So there is a trick where what I said, you can break essentially the space into multiple subspace, which we identify with numbers. So you could do, for example, 10 subspace of 5 bits, in which case you're, let's say, 8 subspaces of 5 bits. You can code each of the subspaces on 3 bits of 5 bit each. So you have 8 bits for the beer header, instead of 8 times 50, which would be 40 bits. So you can compress the bit header at the expense of having separated beer table. You have one per numbering space. So yeah, so they have thought of all those problems, and you can read this RFC, you will see all the details there. So we have seen how packets are forwarded inside routers with beer or with PIM sparse mode, or rather more traditional multicast routing. Now the packets also need to be forwarded via in the local area via networks of switches. And the question is, how we do that? We see that when we are in local area, to send an IP packet, we need to do ARP or neighbor discovery with IPv6. In multicast, we don't do that, which makes sense because those addresses are logical anyhow. So there is a completely static mapping. And for some reasons that are not clear to me, the rules are a bit different for IPv4, IPv6. For example, for IPv6, we mentioned that already. If we have an IPv6 destination multicast address, the MAC multicast address will be simply taking the last 32 bits of this IPv6 multicast address with a known prefix, and similar thing with fewer bits for IPv4 multicast. Which means that there can be collisions. There can be multiple groups that, if they have the same low order bits, they might be colliding in this. They might be distributed via the local area to destinations that don't need them, but that's the price to pay. In fact, things are probably much worse than that in many installations. Here I'm showing an example of a non-smart switch, so the switch you buy for 30 francs at Interdiscount, for example. When you interconnect a number of things, and if I have a packet with a multicast destination address, non-smart switch will simply send them over the spanning tree. It is smart enough to have a spanning tree if there's more than one switch, because otherwise switches really don't work together. But the low-end switches simply send all multicast packets over the spanning tree, which means they are broadcast. It sends every multicast as broadcast. Smart switches don't do that, which is, of course, a nuisance, because if you're watching TV, a football match, which is sent over multicast, then your printer will receive them and will discard them, because it will see the Ethernet adapter of your printer will see, I'm not subscribing to this group. I'm subscribing perhaps to the group of all printers in this local domain, but not of this one. So they will be silently discarded by the Ethernet adapter. Smart switches do like routers. They forward them to the correct destination. But here there's a problem. There is no MAC layer protocol for knowing who is in which multicast group. So we could invent one, but it was not invented. Instead, what smart switches do, they overhear IGMP or MLD. So if the smart switch is smart, it does not just layer 2 analysis of the packets, but it will also see, oh, this is an IGMP packet. This port has somebody who is listening to this group, so I will remember it, and I will do like PIM sparse mode does. It will create, here it's easier because the active topology is a tree. It will decide, for example, that there is, I've never heard here an IGMP or MLD message on this port, so I don't need to forward the packet to this port. And your printer will not receive your TV football retransmissions. IP multicast is a security problem. Of course, if we have IP multicast, we extend dramatically the power of attackers. If you have found a way to do a denial of service attack by sending to all the listeners of something, then with one single packet, then you can reach them. So multicast is of course a problem. This is probably why it is not widespread. It is deployed, as far as I know, only in enterprise or in network. It doesn't cross the boundaries of, does not cross many network boundaries. For example, at TPFL, we can do multicast. But if you are served by Swisscom at home, and if you want to do the multicast programming lab natively from your home modem to EPFL, it will not work because the multicast of Swisscom is only used by Swisscom for their TV distribution. They don't offer, as far as I know, a multicast IP service as EPFL does. One of the reasons is that if you do multicast, then it's much more dangerous. So all multicast capable networks must do exhaustive monitoring and filtering. So if you're Swisscom, for example, and you allow multicast only for your own TV distribution, then you will filter and monitor that only such packets, you know which packets they are, you know from which addresses they come, to which multicast group they should go. So you will not allow any other multicast packets other than the usual local area multicast that are done by IPv6, for example. Multicast has been around for many years. It's even older than IPv6, but as I said, it's not so much deployed, with one notable exception, internet TV distribution. In fact, the original idea of multicast was to replace cable TV networks with IPTV. To some extent, this has happened. You know, very few people listen to cable TV now. Most people, or satellite, most people will use a Switch TV, Swisscom, or Sunrise, whatever. But of course, much of what you get under such program is on demand. So it's not multicast. Right? The multicast is really when lots of people are watching the same channel, which is only for the live channels. So the football match, perhaps you want to see it live. You don't want to see a football match that was recorded 3 hours ago. So that's also one of the reasons, one of the major distribution, internet TV distribution. Another major application of multicast is in what is called virtualization services. Amazon data centers, for example, can create large clusters of virtual machines that are together. And when we say large, it can be thousands of them. So they can create a virtual network, and that virtual network will use multicast. So they can even create virtual local area networks over IP. So when putting together closed network groups, and here, this was, in fact, the main motivation for the development of beer, because those big data centers, when they tried to deploy a PIM sparse mode or dense mode, they found that it was not scalable. Last, as said already, multicast works with UDP, not with TCP, which is also a limitation. Multicast is very, very much used in networks that are a bit underground, not so much industrial networks. Those are networks that we never play with, except if you work in the industry, like Bobst or Smart Grid or companies like this. In a smart grid, for example, when you have a sensor that senses something on the electrical lines, it sends the information typically to more than one destination. It sends it to the SCADA, the monitoring computer. But first, there can be multiple monitoring computers, because for systems that need high reliability, you may duplicate them. And second, there may be also control functions. So the same information may be sent, for example, to trigger closing a relay. If you detect a fault in the line, within a few milliseconds, you close a relay. This is all done by packets that are sent from device to device. But then you may also want not just to do the action, but also to monitor that the action has taken place. So you log the packets. Therefore, the packets are typically received by multiple destinations. When you do small devices, it's easier to use multicast, because you say, I send it to that function. You don't, if you add a monitoring device, you don't need to change the source and the sensor. That's the beauty of multicast. So because of this, this is heavily used in industrial networks. Question? In which context? Or for beer? So the question is how, in beer, I show the cloud where an edge router knows, oh, this destination multicast address should be sent to routers 1, 2, 3. So how do we know that? Well, in beer, there are multiple ways to do it. If you think of beer as being deployed in a virtualization center, then when you design your virtual LAN, you say which routers and which ports are part of this virtual LAN. So in that case, you have a software-defined networking application that knows that because you designed it, you created it. So that's an easy case here. Otherwise, it may be more tricky, and that's the thing that beer does not solve, really. It requires a heavy infrastructure to do this, but beer doesn't solve this problem. But beer solves the problem of the forwarding, the real-time forwarding of packets by multicast routers. It makes it fast. Voila, I think we have many questions, so I will, whoops, going forward. I will skip the quizzes and post the solutions later today, so you can try them. You also have quizzes online, which you can exercise your understanding. And that is the conclusion about multicast. So multicast is very useful in specialized setting, has a scalability problem. And in some sense, we start with multicast to see some of the parts that deviate from the beautiful TCP-IP architecture. We've seen, for example, the beer header. We add a header, which is not really intended in the IP head, in the IP packet. We will see more of that as the course moves on. Voila, that's the end of the multicast part. Without further ado, we continue with routing, but start with more classical routing. What we'll see today is what all routers do, practically, not all, but quasi all routers and networks do, which is called link state routing. So what this figure is trying to illustrate is exactly how link state routing works. This is a description of the entire network. So if you have a network with 200 routers and you have tables, like think of it as an XML description or a database that describes how the network is. Link state routing heavily uses that, is based on this central component. But before getting there, let me say a few words on routing in general. As for bridges, there is also a song, which you can know. Routing, as I mentioned, is part of the data plane, is part of the control plane. And the data plane is what processes packets one by one. There is some ambiguity about the terminology. Sometimes you read, if you go on the internet and you read IP routing, sometimes it means IP packet forwarding. In the context of this lecture now, routing really means not the individual forwarding, not the data plane function, but the control plane function. So the goal of the routing protocol is to automatically give values to the routing tables. Very much like the bridges do. The bridges do their MAC forwarding table completely automatically. We don't call it a routing protocol, but it's the same idea. There are many, many different ways of doing routing, and the most popular ones, the most deployed ones, are link state routing inside a domain and path-based routing in BGP, and we'll see other variants of that. Link state routing, which is what we will discover now, is described in one slide as follows. All routers in one domain obtain a map of the entire domain. So they know all the other routers and all the links between all routers. It's like a Google map, or let's say you have an entire map of the entire domain. And whenever you want to build an entry into your routing table, for every destination prefix, you will compute shortest path to the destination prefix. So it's like having Google Map and then knowing all the destinations that exist in this domain and computing all the shortest paths. This is Ospf. There are other methods. There are distance vector routers that are smarter in some sense, but have convergence problems. So we will discuss towards the end of the course. Of course, having a map requires a fairly heavy information. So it requires heavy processing and some reasonable disk space. If you want really small footprint methods, another one is called distance vector. Distance vector is using a very special algorithm called Bellman-Ford routers inform the neighbors of their own list of distances to all destinations, and having only this information in a message passing way, all routers can compute the shortest path to all destinations. That's a bit magical, but it relies on the fact that it's possible to compute the shortest path on a graph by having only a local algorithm that says to the neighbors, what is my impression, my current estimate of the shortest path. I give them to you, and you update them, and you give me the result of your update, and so on. And that requires much less information because I need to know only my distances and where to go for every destination. I don't need to know the entire map. Router R2 needs to know that for this preface, it needs to know to R5. But whether the network is big or not, every router knows only all the destinations and the next hops here. So essentially, distance vector uses as routing information its own routing table, not more, not much more. Path vector is a bit similar, but here we don't compute distances, but paths. Paths are names of objects. Objects in path vector are typically domains. For example, if you're at EPFL and you want to send a packet to a network in, a local area network of an operator in California, the path will be send it first to switch, then switch will send it to AT&T. AT&T will send to the local operator in California. So you have the name, the succession of all the names or AS numbers, and that's the basis of BGP, which we will discuss a bit later. And then there are other routing methods, lots of other routing methods. For example, source routing, which is an old idea that is used in systems like DSR, ad hoc networks, when Caterpillar machines are deployed on an area to work. They build their own network using this method. The idea is very simple. Essentially, it says that there is no routing with source routing, strict source routing, like presented here. There is no routing table. All the routing information is put by the source in the packet. Here, I'm illustrating a packet that A wants to send to B. Through some mechanism that we'll discuss in a second, A has found a path to go to B, and this path is A, R1, R2, R4. Right? So A, after knowing the path, will put it in the packet header. There are various ways to do it, but the smartest way is to put as destination address the next hop, and the rest as an extension header. So this packet will be sent to R1. R1 will receive it, and will know there is a strict source routing header. So it knows it's not the true destination, but I need to send it to R2, a bit like the beer header that we've seen before. So the header will be modified. The packet is therefore sent to R2. R2 will receive the packet, send it to R4, and it will go this way. The jobs of the routers with this are very simple. This is why it is used for what is called ad hoc networks, when you deploy in the field a number of routers and you want them to discover autonomously the routes. There is a cost, of course. All the burden of routing is put on the source. That's why it's called source routing. How can A know this path? Well, the traditional methods in such systems is to send source discovery packets. So A will first flood the packet to B, and this so-called exploratory packet will record all the paths. So the packet will send to all the neighbors of A, R1 and R2. R1 will rebroadcast the packet to all neighbors, but the packet records the path. So R1 knows it's come from A, so will not send it to A. It will resend it to R2 and R3, etc. So there can be a fairly large number of combinations, but this is for small networks. And we avoid loops because every packet contains the accumulated path, so you don't send it back to an element that is already accumulated in the path. So after that, B will receive a number of paths, probably 1, 2, 3, 4. So B will receive 4 packets and will revert the paths and pick whatever B prefers by whatever algorithm. Perhaps the first one that is received, that's an indication that it was the shortest path, and will reverse the path and send it to A, and now A and B know a path from A to B. That's the method which is called with what is called strict source routing. Here it's called strict. It means that the routing header contains exactly the list of all the hops. If the network has changed, or if there's an error in the list, then it will not work. The packet will be lost. You will need to send exploratory packets again. In the internet at large, sometimes in some specific contexts, we use another form of source routing, which is called loose source routing. Here, the intention is a bit different. The idea of loose source routing is that we want to force a packet to go via certain intermediate hops. When you use Google Maps, it's the via part of Google Maps. For example, here, assume that A wants to send a packet to B, but it wants that the packet must go via R4, R2, and R5. Why do you want this? Well, typically, it is because you want the packet to force some, to go to some routers where there will be, for example, packet filtering, deep packet inspection. So if you want to force, because B is a suspicious destination or A is a suspicious source, then whenever the edge router receives traffic from A, it may force it to go via R4. So the semantic is a bit different, but the idea is the same, except now that we assume that there is unicast routing that already exists. So A is able to send a packet to R4, and R4 will do the same thing, will analyze and change the header to eventually reach B. This is what is called loose source routing. It is, for example, used when we use mobile IP. One way of using this, as I mentioned, is for forcing packets to go via some destinations. Another way is to force, when I have a packet that you send to me and I'm moving and my IP address changes, then I can use source routing to use whatever is called the care of address, the address where I am now. I put it as a source routing intermediate address. That means in order to send it to me, you send first to this address where hopefully I am now. So that doesn't change my destination address, but that forces the packet to go to a specific place. As you can imagine, source routing is also very dangerous, even more dangerous than multicast, because anybody who can manipulate the source routing headers can do traffic diversion, can capture traffic and easily control the network. So because of that, source routing is not used in the public internet. It is used, and what I said of mobility works only in very specific scenarios. Source routing today takes the form of what is called segment routing, where we go even one step beyond. And instead of putting here an IP address as a destination, we put a header that is a pointer for the router to do some specific function. For example, the function might be forwarded to a next hop, but it may be also do something specific to this packet, like inspect it more deeply. So this is also typically used in data centers. So source routing, loose source routing, segment routing are used in closed environments like data centers. Voila, that's all we will see for this first hour. So we do a break now and resume at 1:15. After that, we will dive into the details of the most popular routing protocol inside domain, which is Ospf. So we are now in a single domain. Domain means here an entity that is managed by a given organization. EPFL is one domain. Google is one domain. Of course, if the domain is very large, perhaps you will split it into subdomains. And we heard when there was the Facebook crash a few weeks ago that Facebook uses BGP, for example, inside its own operation. But I mean, it is so large that it treats itself as multiple domains. A domain is typically perhaps 1,000 routers, but not more. Inside the domain, the most popular routing protocol is Ospf, which itself has multiple levels of complexity. So we will start with what we call a single area. Inside a single area, we do link state, which is what I described before. Every router will acquire a map, which is called a topology database of the entire network. In order to acquire this map, then a router must first bootstrap the information from local information. So every router has its own information about whom it is connected to. So it's called the local interface database and the adjacency database. So the interface database is what we have when we do ifconfig. And the adjacency database is what we obtain if we are a router by sending hello messages on the link. So if a router is in principle configured to have a link that is used for running Ospf, hopefully there is another Ospf router at the end of this link. So the Ospf router will discover this automatically. So all of this is automatic once you have configured if config, for example, the IP masks and so on in your routers, OSPF will run automatically. You will do that, discover this in the lab. That's the goal. OSPF should not need an external application to come into the router to give what are the routing tables. The major reason we do this is that it's very hard to do that externally, to go into a router externally. Because in order to do that, you need to be able to go into the router. So you can physically, with your bicycle, go to the other end of the campus and take a USB key and a laptop, USB cable and a laptop and go into the router and configure it. If you want to do it remotely, then you have a chicken and egg problem. You cannot configure the routing tables remotely unless you find a very smart trick, which we haven't found today. So the goal here is really to have the thing being learned automatically. Very much like what we've seen with the spanning tree bridges. They discover the spanning tree, or they make a spanning tree autonomously. And we would have the same problem if we need to go into every bridge to do it. We first must be able to talk to every bridge. So the first thing is the hello protocol. And this is, the details are very complicated, but the idea is very simple. Hello means every few seconds you send a message and you're expected to reply to this message. And if you receive the reply, you know there is a router. If after a number of hellos, you haven't received no reply, you declare that the other end is dead or doesn't exist. So once two routers become new neighbors with the hello protocol, they first synchronize their link state database. The link state is a topology database. That's the map of the network. Synchronize means they will merge the information that they have. Perhaps, for example, they become neighbors because the network was partitioned and now they are reconnected to each other. We'll see an example. But typically, one router is new, has very little information, and the other one is old and knows stuff. So the new gets from the old the information that was available. Okay. Let's see on this example here. The only difficult thing is or non-trivial thing is the terminology. So link state advertisement is the key concept in OSPF. That's the database record, if you want. OSPF doesn't use database technology like MySQL or whatever, but we can think of it as a database. So these LSAs are the records of the topology database, and they are sent. They are originated by one router, where one router describes what it sees locally, and then they are flooded to the entire area. And of course, we avoid flooding loops by first having a sequence number. And whenever a router has received an LSA, it must remember it because it must build its own view of the network. So it will record it. And when it sees an LSA, it will check whether it's not already present in the database or it has a sequence number that's older, that's one in the database. Then it will not reflood it if it has already been received. Let's see an example. Here is my toy network. I have 1, 2, 3, 4, 5 routers. Later, there will be a 6th router that will come. And the routers are connected via point-to-point links. Those are those drawings here. Or shared media links, which are in fact networks of switches, local area networks. Here we find again that the vision that IP continues to have, that IP is interconnecting local area networks. And local area networks, the prototype is Wi-Fi or Ethernet. Those are shared media networks in particular. By sending one packet over an interface, you might reach one, but possibly also more than one routers. So that's our view of the network here. And every router knows by configuration its local information. For example, B knows that it has a port that corresponds to a network prefix N3. And it shows an Ethernet port here. And then you must configure also whether this port is supposed to run OSPF or not, whether you expect to have routers on this port or not. If not, it's called a stub network. That means that stub means the end. Otherwise, there are ports on which, like N2 and N4, on which you expect to see other routers. And then you give them a cost. You give them a cost because you will compute shortest path routing. It's very much like the spanning tree protocol. If you want to give them a cost, you can give the cost you want. Otherwise, there are default rules to give costs that are larger to technologies that have smaller bit rate. So at the beginning, every router knows only this here. Then B, when you start the OSPF process, will simply send an LSA, which is a copy of its own information to all its neighbors. So we'll send it to A and to C. This LSA contains this information that we discussed. It says, I am connected to N3, N2, and N4. And also, I have before that, I should have mentioned B, before doing that stuff, must have synchronized with B and C. So at the beginning, they have nothing to synchronize. But at the minimum, with the hello protocol, B knows it's speaking to A over N2, which is reflected here. So B knows it is connected to a router on N2 and N4, and that's its local information. And then this is flooded. The message is sent to C and A. When C receives it, it sends it again on this interface. But when A will receive a second copy, if that comes second, A will simply ignore it because from the number that is the sequence number of the LSA, it knows it has already received this information. And eventually, this will be flooded. So flooding is a very simple protocol. Everybody will receive it. At the end of this process, all routers will do the same, and all routers will have all the information that is shown here. That's the topology database, or also called the link state database at all routers. So all routers will have the same. So B knows, for example, has the information it knows already locally, but it has received this information from A, from C, from D, etc. So the first thing to remember is that at the end of this process, which comes very fast because sending a few messages to routers is quasi-instantaneous, and flooding them to all 5 routers here have the same information there, which is in textual form, the representation of the drawing that I have here. There's a small subtlety here that if you see here, B is saying, I am connected to A and to C, but what does C say? C says, I am connected to B via N4. This is this line. I am connected to D via N5, but for N1, it simply says, I am connected to N1. It is not saying I'm connected to A. This is because OSPF had a problem, which is OSPF uses shortest path. Shortest path is an algorithm for graph. On a graph, we must have nodes, and between nodes, we have only one edge or 0 edge, but not parallel edges here. And a node cannot be a neighbor of several at the same time here. So here, the way this is addressed, when we have C is connected to A, but there might be another router, or might be 100 other routers that C is connected to via N1. The way OSPF addresses this is by giving a personality to local area network. In OSPF terminology, it's called a multiple access network, like N1. N1 will be considered by OSPF as a node of its own. So if you want the switch, which is not wrong, there are probably lots of switches that make N1, but the switches don't speak OSPF. They don't do IP net layer stuff. So instead, one of the 2 networks, A and C, or if there's more than 2, will speak for the switches, and it is called the designated router. So when A sees an interface, it sees, is it a point-to-point interface or is it a multi-point interface? If it's multi-point, which is typically the case for Ethernet, A with the hello protocol will not just discover C, but as a result of the hello protocol, one of the 2 will be elected the speaker for the network N1. The designated router in this case is C. And OSPF will do, C will say, I am connected to N1. And then C will speak for N1 by sending an LSA from N1, as if it would be coming from N1. So N1 will say, I am an Ethernet. I have a cost of 0, that's the usual convention. And I have a number of routers that are directly connected to me, which are A and C. That's the only subtlety that there will be here. Now let's continue, because I've shown a very hypothetical case where the 5 routers boot at exactly the same time. In reality, that never happens like this. What happens is they boot one after the other. Even if they boot at the same time, well, everything will not be happening at exactly the same time. So there will be some arbitrary order that will happen. Let's assume here, for example, F now boots, and F is connected to N7 and N1. What will F do? Well, with the hello protocol, F will synchronize with C and will also synchronize with E. Synchronization means, first I will discover that C exists. I will also discover that C is a designated router. And synchronization means C will send to me, F, all the database that it already has. So from the previous slide, here, all this information that C has now will be passed to F, so that F does not need to wait until the LSAs are refreshed by B, etc. So that we have a very quick, up-to-date information in F. F will do that, and when they are both synchronized, when they both know that they have the same information, F can start sending its own local information, that is new information. For example, F knows it's connected to N7. The same might happen with E. In fact, it might happen before. Here I'm assuming this happens with C first. Then F will, after being synchronized, send the information to E, to C, that will then flood it. And then we will see in red at the end what all routers will have. We'll have new information from F, which is F is saying, I am connected to N7, which is an Ethernet, and I am connected to N1, and N1 is treated here as a multi-point with designated router C here. And same thing from E. Here the designated router is E on this multi-point network. C will also need to send an updated information, not because anything has changed in C, but because C as a designated router speaks for N1. And things have changed for N1. In N1, there's a new router, so there will be a new information from C here. So at the end of the process, if there is now no change in the network, this is how all the information will be available in all routers. Yes? Yeah, that's a typo. It should be there too. It should be there too. Yeah. Good catch. This is the graph that Ospf sees. We see that routers like networks like N1 and N7, perhaps N3 also, are treated as nodes here. And C is designated for N1 and E is designated for N7 here. And to avoid duplicating the costs, you need a rule so that if the interface C has a cost of 10, then you don't make it 10. For example, the cost of going from C to A should be 10. So one common rule, which is not mandatory, but the default rule is that the cost from a network to a router is set to 0. So that's the view that Ospf has in reality of this network. Now we have a standard graph, so we can do graph theoretic stuff. And in particular, the next thing we'll do is to compute shortest path. Now, if we do Wireshark of Ospf, we will see that Ospf exists as a standalone protocol. It's not using TCP or UDP or something else. It is a standalone protocol that immediately exists on top of IP. So there's an IP protocol number for Ospf. This is this number, 59 in hexadecimal. There are different versions of Ospf. The current version is version 3, which supports IPv6 and dual stack networks, but does not support IPv4 only. So if you have a network that is IPv4 only, you should use the version 2. Ospf routers need a number, like I put the letter ABC, so they typically have an Ospf number, which has the same format as an IPv4 address, but is not necessarily an IPv4 address. Now, the goal of all that stuff is to compute next hop. That's all. We want in the routing table to know how do I go from me to a given destination. This is done by Ospf by default using shortest path routing. So now that every router has its link state database, it has a complete Google map of the network. So if it wants to go to a destination, it will simply compute the shortest path. There are variants to that. If we have a map, we can not simply compute the shortest path, but we can add other things. And Ospf is very rich and is used in lots of things. For example, you may want to compute the shortest path that has a delay less than 50 milliseconds. If you know, for example, you have satellite links that have long delays, So you can add attributes to links that may influence the computation of a path. All of this is possible, but we will not go through that in detail. We will simply compute the shortest path, which in itself is complex enough. So paths are computed independently at every node. So this is where the nodes diverge. All nodes have the same topology database, but they don't do all the same computation, because what we compute is all the paths from me to everyone else. A router does not compute the path from router A to router B. I don't care. So all routers compute shortest path trees that are rooted at self, which means at the end, they all compute different things, even though they have the same topology database. This is the algorithm that is used in Ospf. It uses Dijkstra. Dijkstra's algorithm is the so far best known algorithm for computing shortest path from self to a number of destinations. We'll see that the distance vector uses another algorithm. It's less efficient for this job that I just mentioned, but has other properties, which is Bellman-4. We could use Bellman-4 in Ospf, but the complexity of Dijkstra is less, so we will take fewer CPU cycles to compute the same thing. This is a very simplified, not simplified, this is the full version of Dijkstra. It's a bit complicated because we want to allow multiple equal path costs. If you do in a network, very often, if your network is a ring with 4, for example, there are 2 paths to go from one end of the ring to the other. They have equal cost. In the spanning tree protocol, we would forbid that. We would take only one of the best, when the bridges compute the shortest path to the root, they always take only one. If there are 2 equal path paths, they use whatever tie-breaking rule to pick only one. In routing protocols, that's the opposite. We're happy to have multiple paths because that gives more throughput, that uses the capacity better. And if one path breaks, at least we don't lose everything. So that is the complexity of the algorithm, because we want to record not just the best path, but all the possible best paths, up to some limit, of course. Dijkstra is a very special algorithm. It's called greedy, in the sense it computes at every step the best known information to some destination. And this best information so far is the best forever. So the only thing that changes is we might not know for a given node where to go, but at step K, if I know something, that best thing will not change. And that is a bit miraculous. It's an outlier in the family of algorithms, but that's how it is. So Dijkstra uses a set that it increases, which is the set of nodes visited so far. So how does it work? At every step, so it starts with the empty set, then at every step, it adds one node, one router. We've seen it's not just, the node can be a multi-point network. It adds one node, which is the node that was not yet added, that minimizes M of I. So M of I is the estimate we have now to go from self, which is node 0, to node I. So, and these estimates are the estimates I have by visiting only the nodes that are already in the visited set. So that's a chicken and egg definition. I think the simplest is to look at an example here. Here I've simplified the network we had before to make the story a bit less complicated. Here I have a network with 6 nodes called A, B, C, D, etc. The costs are shown on the links here. I assume they're the same in both directions, which is not always necessarily the case. And here I'm showing and we are at node A. So topology database is the same everywhere, but we need to say at which node we're doing the computation, because now we want to compute shortest path from A. Then the values that we have, M of something, is our estimate of the distance to go there. So of course, to go from me to somewhere, the distance to me, the cost is 0. And at the beginning, when we start the algorithm, the cost is infinite to go to everywhere because I don't know where to go. And initially, the set of visited nodes is empty. Then I will pick among all the nodes that are not yet visited, the one that has the smallest value. Then the first step is, of course, obvious. I will pick A. So in the first step, I will add the self where we are. And when I have done this, I will update my estimate of the distances to all nodes by saying, what is the distance of going to all possible destinations via the pink nodes, the nodes that are already visited. Here, there's only one, there's A. So the cost of going from A to B is 100. That's the link that goes there. The cost of going from A to C is 10. So we put the value 100. M of B becomes 100. M of C becomes 10. The cost of going to F is 10. And D and E, I don't know them yet. So their costs are infinite. Now, when I do that, I also record the arrow that says, what is the shortest path to go to B? Now, there's only one path. So to go to B, I went from A to B here. That's this red arrow is saying, the shortest path from A to B goes via this link here, which in the first step is trivial. There's no such choice. Now, step 2. Step 2 is more interesting. I need to add one node, B, C, D, E, or F, which is the one that has the smallest estimated distance. Now, the estimated distance are those values here. Now, there are C and F. So I pick one of the two. I must pick one of the two here. I will keep multiple paths, but at one point in time, I need to add only one node. So I decide, for example, to add C. So I will add the node C. So the visited set is now A and C. Now, since I have added C, I change my estimates of the distances. For example, for D, what's the distance of going from A to D via one of the visited nodes? So there is a distance. Previously, the distance was infinite, but now I have a direct link from C to D with a cost of 20. So the cost of going from A to D is now the cost of going from A to C, which was 10, plus 20, which gives 30. So I add 30 here, and I add an arrow, which goes how it goes there. Now for B, it's a bit more interesting. I have now another path to go to B, because B is a neighbor of C. I knew before I had a distance of 100. I compare the new thing I have. The new thing is 10, that's the value I have here, plus 100, that's 110. That's less good. So this new path is not used. It does not improve the distance going to B, and the red arrow remains where it was before. If here I had 50 instead of 100, I would have discovered a better path. The M of B would become 60, and the arrow would now point in this direction. And for F, there's also the same thing. We can go via F to F via C, but 10 plus 10 gives 20, which is larger, so nothing has changed. So we see those arrows that gives also the predecessor sets and the visited set here. Now, next, I will add the next node that has the smallest cost, which is F. So I will add F. And similarly, I will improve the distance to B. In fact, that's the only thing that will improve here. B is now at a distance of 20 from A, and I've also updated the predecessors. Now, step 4, it's up to you to do. For step 4, which will be the next visited node. Is anything showing up on Speak Up? Yes. Okay. I don't see anything, but okay. So I close the poll in a few seconds. Well, I don't see any results. I'm not sure what has happened with Speak Up. But the correct answer is C. which is the node E. So node E had 20, of course, we added. And here the interesting thing becomes what happens for D. Now for D, we have a new path that has a cost also of 30. If I go via E, E is at a distance of 20 now. So E will do the Dijkstra algorithm that says for all the neighbors of D, update their state. So for D, all neighbors of E. For D, we will see that we have 30. This is not improved, but it has an equal cost, which means I have a second path of cost 30 here, which is added. And we see that the predecessor of D now is a set with two elements, C and E, which corresponds to the fact that there are two equal cost paths to go to D. So this is what will happen at step 4. At step 5, D will be added. That will not change anything. And at step 6, B will be added. And that's the end. We've covered all the nodes. And this is how it works. This is how Dijkstra works. What is far from trivial is why this works, why this does give the shortest path, but the proof is well known and will not go through it. That's the final state. I mentioned it's a greedy algorithm because we see that whenever a node is visited, its estimate of the distance doesn't change. Right? So whenever I add B, for example, I don't change any of the nodes of the values that are already visited. So we visit nodes one after the other, and the value we obtain for those nodes and the predecessors of those nodes that are visited are never changed here. Greedy algorithms are very rare, right? We love greedy algorithms because their complexity is very small. It's linear in the number of nodes. We visit nodes one after the other. We never need to backtrack or to iterate. Message passing algorithms like Bellman-Ford have quadratic complexity in number of nodes because you need to pass a message and back and forth. Here, at every step, you do at least in number of nodes. If we count complexity 1 of one step, then it's linear in the number of nodes. The goal of all that stuff is to populate the routing table. So to know, for example, from A, how do I go to every destination? Again, this entire exercise is useful only for A. So the only thing that we distill out of this very sophisticated representation is the next hop for all destinations. So if the destinations are, for example, D, in order to go to destination D, A will know that there are two paths, which are ACD, AFED. How do we know this? Well, we go backwards from D, following the arrows in the reverse direction. We know that there are two paths, and then we just collect what we do at A. So at the end of this, the only thing we distill of this algorithm is that at A, in order to go to D, the next hop is C or F. That's all that we will remember from that, from this algorithm. That will remember from all those results. What I have presented is not exactly what Ospf does, because as you can see, my presentation is a bit clumsy. It's optimized to be easier to understand, but of course we don't put red arrows in things, but and pre-process the nodes going backwards. It's possible to write the next hops in parallel. So this is what Ospf really does. So it computes the next hop in parallel, which makes the thing a bit more complicated, but essentially doesn't change the idea. So if we take the network we had here, and if we are at node A, so the network is a bit more complicated, but at node A, this is what Dijkstra will give. It will give the cost and the next hop for all the destinations that are not on link here. There are a few optimizations we can do. For example, if we know here I've presented, in fact, a biased version of things as if the destinations would be routers. In reality, the destinations are not routers. The destinations are prefixes. Prefixes are IP prefixes, for example, like N3. B says to all the networks, I am connected to N3. I show only one prefix and many intermediate links. But in reality, that's the other way around. Usually there are many, many prefixes that are at the edge and a small number of intermediate links here. So, because in order to go to a network like N3, for example, we must go via B. So, sorry, so the first thing to say is that what Ospf will give in the link state database is all the prefixes that are reachable. So all the things like N3 will be available in the link state database. So all routers like F knows that N3 exists. So it will give all the prefixes that exist in this given domain. But of course, if this number is very large, which is typically the case, you don't want to run Dijkstra with a network where there is one node for each of those. For example, because imagine there's 1,000 prefixes that are connected to B, then they're all called so-called stub networks. You remove them from the Dijkstra computation. You compute first how to go to B, and then the algorithm to compute the routing table will say, I know N3 can be reached only via B. So when I put N3 in the routing table, I will first go to the routing table to say, how do I reach B? Then I add the cost of going from B to N3 here. All nodes will do this, and that will dramatically reduce the number of nodes. We have seen in this example that in order to reach D from A, there are two possible paths here. And we want to do this. Now, practically, when router A has packets to send to destination D, what do you do when you have a table that gives you several possibilities here? So what is your preferred choice? Do you see a speak up poll? Okay, you do, I don't. I close the poll in a few seconds. Oops, closed. Do you see the results? No. So this is not so useful. So what are the things we could do? Send them to next hop randomly with equal probability, or send one next hop and send all to them, or test the availability of the next hop before sending. Well, testing the availability of the next hop before sending is probably something that Ospf should do with the Hello protocol. So probably that's not a good option. But the rest here is not so clear. So what is the correct answer? Let's see here. Well, the first thing is if you have multiple hops, it's better to use them all, right? So it's a good idea if you don't have any other criterion. We can change the criterions with some additional mechanism, but if you have no other reason, then you send them with equal probability. But there's a problem with our good old friend TCP of a few weeks ago, right? If we send multiple hops, then we'll see that fast retransmit, all that stuff, might think, oh, that the packet is lost because the hops have different latencies. So this is a strange place where the original design of the internet, which allowed this multiple hops for reliability, making the network survivable, and also improve the performance, comes with a conflict. So this conflict is solved, conflicts with the way TCP is designed. We could fix TCP. That would be perhaps the healthy thing to do, but this is not what is done. Instead of that, we do what is called per-flow load balancing, where the router will determine the flows by looking at the port numbers. We've seen that NATs do that. So by now we see that almost everyone in the internet does it, looks at the port numbers of the source and destination, or only simply the source and IP addresses, depending on how this is configured, hash the resulting flow identifier, the result by also obtaining a number between 0 and 1. If it's a good hash function, doesn't have to be a cryptographic hash here. It just needs to be a hash function in the sense of the distribution of the result should be uniform between 0 and 1. So uniform in the sense of probabilities, which have a uniform distribution. So it's equal, it's anywhere between 0 and 1, and with equal probability, it is everywhere the same. And then, well, if you have two next hops with probability 0.5, you want to send it there. By the way, that's one way. If you have a pseudo number random generator, that's one way to flip a coin with a computer with probability 0.5. Here, except it's not random, it is deterministic. Two packets that have the same flow identifier will always result in the same choice. But in average, if the hash is truly uniform, we will do the correct thing. So this is how equal cost multipath is typically done in the internet. It can be in the lab. We will see that it can be enabled or disabled. Last, one of the most important things that routers must do when they use Ospf, the value of Ospf, is to be resilient to changes. Changes to the topology, which may occur because a router crashes or a link crashes, or also a router is added. So by doing that, we avoid the Facebook accident, for example, of a few weeks ago, where in Facebook, they put the routing function not with Ospf, but with an outside application, at least for parts of the network. If there's a bug in this application, then you lose the access to the routers. So you cannot fix things because you've lost access. So again, we find the thing that the routing protocol is very important because it is, if you don't have it, you cannot do anything in your network. So in particular, it should react to changes to topology here. That's the primary requirement here. How does it work? Well, simply by updating the topology database. Whenever a router sees one change, any change, then it floods again a new information with the new value of what it sees here. For example, if a network has a new neighbor, it will add this information. We've seen that when F was booting, for example. But if a network loses a neighbor, it will send an updated LSA, and this updated LSA will replace the previous LSAs that existed. And whenever the database changes, that triggers recomputation of Ospf, Dijkstra's algorithm. Of course, what I'm not saying is that there are, one of the beauties also of Dijkstra is that there are incremental, it's possible to compute it incrementally. So if you have analyzed a network and computed all the shortest path, if you change some local information in the network, it is possible to compute it incrementally, to recompute incrementally. You don't have to rerun the whole of Dijkstra. We will not see that in detail, but that's one of the reasons also for having Dijkstra. Let's see here, assume the link between A and B breaks. So what I'm showing here is the state of the routing tables at the 4 routers, and on the left, the topology database. In a very pictorial form, topology database is simply a picture of the network here. Now this link breaks. This will be detected by A. How does A detect it? Well, there are various mechanisms. Certainly the hello protocol will detect it once in a while. The hello protocol is typically not very fast. So what there is very often on most networks is called a beaconing protocol, where, for example, on every 10 milliseconds on every link, A sends a keep alive message to all the neighbors. And if I think more than every 3 milliseconds. And then if 3 times in a row the message is not received, A does not receive this message from A, then it will detect that the link is lost. Sometimes you also detect the loss locally. For example, if you unplug if the cable is physically cut, your Ethernet adapter will sense that the cable is cut. There is no more power that is coming from the other end. So it will also detect the loss. So there are physical layer mechanisms. There is this beaconing mechanisms, the BFD mechanism, and there's a hello protocol. All of those 3 may play together or one after the other. So A detects that this link is broken here. So A now sees that its local vision of the topology database have lost a connection from A to B. So A will delete first all the relevant parts of its routing table. There's no point going to B because now B is lost here. A will rerun Dijkstra on this new topology database and will, for example, find that in order to reach B, I need to go to C, which is what this topology says here. So the next hop from B is C. And A will inform C. All of this will happen in parallel. I'm not sure which one will happen first. It's typically multi-threaded. So A will send the message to C with a new value of its own LSA. So C will receive that, but C does not have it yet. So at this point in time where we are now, there is a loop in the topology in the routing here. So if C sends a packet to B, there is equal cost multipath, but C might send the packet to A. Now A will send this packet back to C. Ospf is in the control plane. The loop is in the data plane. So in the control plane takes some time. It involves the processor of the router, which is like a processor like we have on our computers, whereas the data plane is using dedicated hardware that forwards the packet very, very fast. So this loop exists. There might be packets that are caught in a loop between A and C during the time that it takes for Ospf to process and do the job that we're saying. That's an example of a loop that can exist in IP. And because we accept that such loops can exist, we have the TTL field in IP and the hop limit, the hop count field in IP. By accepting that such loops exist, we make Ospf simple. In particular, we don't need to synchronize all the network. Synchronization is a tremendously complicated thing to do in a distributed system. If you want to force all systems in a distributed system to do some actions only when they all have reached the same status and they know that all others also have reached the same status, it's called consensus. And the consensus protocol is very heavyweight. In fact, if you don't have timers and messages are not reliable, it may take no guarantee, there's no guaranteed time to converge. Here we do radically different things, which is very typical of networking. We do things that must work and are much more robust. So here we accept those temporary loops. We don't want things to synchronize. Now, of course, sooner or later, C will receive it. C updates its topology database, updates also its routing table. Now it knows in order to go to B, there is no longer this there's only one path, the one that goes via D here. Now there's no routing loop, but traffic that would send from B to A, for example, will die on the link. And there is still a problem, traffic that D sends to A, for example. D doesn't yet know of the problem. So D might send 50% of the traffic via this way, and this traffic will be lost, which is fine. We accept that. We hope that Ospf will recover. While Ospf is recovering, there might be bad things in the network. There might be loss of availability. That happens in the internet, but we know that packets can be lost, and TCP and all applications should survive the loss of a packet. Then sooner or later, B will also detect the loss. Here, I'm assuming it detects it a bit later. So updates everything. Its topology database, recomputes Dijkstra, and updates its routing table. And it will also receive an information from A, from D. Here, the LSA from A is flooded by D and reaches B. And at the end of this, now we have the network has converged again. So all the 4 nodes have the correct information, and the routes are stable again. So if the failure is not corrected, the network will live with this and will automatically have reconfigured, which was the goal of Ospf. Voila, that's the end for today. Next week, we will see a few other dimensions to Ospf.